Hello all, and good afternoon to everyone, and welcome to our webinar today. So today I'm going to talk about failure analysis, and especially how failure analysis is conducted as a part of reliability analysis. My name is Laura Frisk, and I'm the CEO of Trellick. And in Trellick, we quite often do lots of failure analysis, so this is a very important part of our work. And today I'm going to talk about the basic methods we use, and also why failure analysis is so important. Before I go to my actual topic, I will very shortly introduce Trellick and what we do. Trellick is a company based in Finland, in Tampere, and we work a lot with different companies in matters related to reliability and different materials, and how different structures should be used to make sure that your product is reliable. So we do lots of testing, lots of analysis, and also material characterization. And we mostly work in electrical engineering and also with plastic materials, but more and more also with other materials and other structures. So here is quickly our areas where we work. So we do lots of reliability analysis, as I said. Failure analysis is very important. So we do lots of failure analysis as a part of product development, but also quite often when something fails in the field, we do analysis to find out why it happened and how it could be fixed. As I mentioned, we work a lot with different materials and their properties, especially with long-term reliability of materials. And next week, Sanna is going to give a webinar about that, so I highly recommend that. And we also work with electronics assembly, mainly with new flexible and wearable electronics, and where we have one EU project actually ongoing at the moment. So, but today, as I said, I'm going to talk about failure analysis. So I will start with why it is important to conduct failure analysis, and also about the terms and kind of what is meant by failure analysis. Then I will talk about stressors, so what causes failures, and also about failure mechanisms, and also about analysis methods, although in the next week, as I mentioned, Sanna is going to talk about material characterization as a part of failure and reliability analysis. So in some areas I will be rather brief. And then finally, summary. So why do we do failure analysis? Well, if we consider failures, everything fails if we expose things to hard enough conditions. Now, when we have a failure, it is important to know why the failure happened and how it happened. And this is so that we can determine whether the failure is actually important and critical. So do we need to do some corrective actions? And if so, what are these? Sometimes the failure can be just random or something due to misuse or something like that. And maybe in that case, we don't actually want to improve the product, maybe give better instructions how to use the product. So it's very important to understand why the failure has happened to be able to do the right or take the right actions after that. And to understand why things fail, we need to conduct a systematic study about what happened and what affected the results, and what are the main reasons for the failure. So failure analysis is used, as I already said, to find corrective actions, what could be used to, for example, improve the reliability of the product, but also, as I mentioned, also to give better instructions, for example, to use to prevent failures due to misuse and so on, or for example, due to wrong storage conditions or something like that. It can be also used to improve manufacturing processes. So sometimes we see failures already during the manufacturing, and then we can check, for example, why this happens. We can maybe change the processes and this way improve it and make it more reliable. Of course, in many cases, it's extremely important to understand how and why failures happen, to prevent something bad happening. So there are high risk applications where we cannot have failures. So it's very important to analyze failures already during the product development to see what kind of failures we might have and so on. And of course, we want to reduce the financial costs due to bad reliability and due to failures in the field. Sometimes you also need to meet some standards or regulations, and due to this, there needs to be some analysis done. And finally, unfortunately, sometimes when you have a complex product and something fails, you need to also check who is responsible for failure. So who takes the responsibility? This, of course, is not very, very nice when this happens. So when we talk about failure analysis, there is lots of terms which are used. What I've seen is that people with different backgrounds and different education tend to use slightly different terms, and sometimes it's very important to check what people mean by different terms so that you can be sure that you are talking about the same thing. However, of course, when we talk about failure analysis, it's first important to determine what is a failure. So basically, we can say that the failure is an inability of a material, component, device, or process, or whatever we are doing, to function properly and as it should. And what is a failure depends a lot of the application. So sometimes it's really obvious. So if we have an electrical product and it doesn't turn on at all, we know that it has failed. Or if we have a LED lamp that doesn't function, of course it's failed then. But sometimes it's not that easy. And for example, we work a lot with subsystems, single components, maybe even just materials or something like that. And then it might not be that clear what is a failure. For example, what is the limit if our system has some fluctuation in its properties? So where is the limit when it's still okay, or when do we consider it a failure? So it is very important to, of course, determine what is a failure and how it's defined, and for all products, especially if you are doing failure analysis, so that you know what has been determined as a failure. And when we talk about the terms, as I said, there are different terms used. And for example, physics of failure is quite often used, and it's more like there is a definition shown here. It's a rather long one. I'm not going to read it, but it's more like a science-based approach where we are using different tools, for example, modeling or simulation or different analysis techniques to really understand why the thing failed, what are the phenomena behind the failure. So this is very scientific-based approach, and it's quite often called physics of failure, and it's related to failure analysis. So they are kind of part of the same process. Then quite often people use root cause analysis. For me, at least, it is more general term than physics of failure, which clearly is about the physical side of this, or about the scientific part. And root cause analysis can actually refer to any process where we want to understand why things went wrong and what is the reason for that. And at least for me, it's more about the emphasis is in eliminating and correcting. So finding the reason and then correcting that. But quite often, root cause analysis and failure analysis and even physics of failure are caused to mean the same processes. So about some other terms, so failure mode is how we observe a failure. For example, if the lamp doesn't turn on, so we see that the failure as the light there is no light. or a computer does not, for example, the display is not working, we know that, okay, this is how we see the failure happening. And then failure site is the location of the failure. Sometimes it can be very specific, sometimes it can vary. So there we have similar failure, for example, due to corrosion, but it can be found from different sites of the same product. And the failure mechanism then is the actual reason for the failure, the actual mechanism, whether it's physical, chemical, thermodynamic, dynamic, or something else, which caused the failure. So in order to know the failure mechanism, we really need to go into details in the analysis to understand what's happening and what has happened. And the stressor is the reason, is this kind of stress which causes the failure. So from this, I'm next going to talk about the stressors, so the reasons for failures, and then also about the failure mechanism, so why we see, what kind of failures we see due to different stressors. But before going to the actual stressors like temperature, a few general words about failures. So we have several reasons for failures, and of course, because we're using so many different products which have so many different materials, components, devices, so on, we have a huge number of different mechanisms which can lead to failure and different combinations of these. There are several reasons why failures happen, so it's not just the use environment where we might have some issues like humidity or high temperature. It's also how the product is made and used. So the first part, for example, can be the manufacturing, which I already mentioned. It is quite often the reason for the failures that we have some issues in the manufacturing which causes defects. There is some variation. There might be also some changes in the batches. For example, if you buy material, one batch is different from the other, and this causes then issues even during the manufacturing or after that. Then we have transport, storage, and operation conditions, which all can cause failures, either due to wrong storage, for example, but also if everything is correct, it still can cause failures depending of the application and how well these conditions have been determined when the product is designed. Then, of course, when we consider why things fail, we have poor design, poor material choices, or poor quality of materials and components. So there are several reasons why we can have these issues. And of course, then finally, use and wear, which are kind of the natural processes when we are using anything which cause failures. So then when we consider the stressors and why failures happen and how they happen, it is important to consider that there are two ways we can have failure. And one is by overstress. And basically this means that we exceed a critical limit of something, for example, a material, structure, component, and this causes sudden failure, which is due to, for example, if we go to too high temperature and material partially melts in a product, this causes catastrophic failure and the product fails due to this. It can be anything else too. It could be, for example, in electrical systems that we have just very high voltage value, which is over the limit there should be, which burns the component or something like that. And overstress is normally, in manufacturing, this is quite common, that we have situations where the manufacturing requires very high temperature, for example, and this may lead to overstress failures, not necessarily though. And of course, it is always important to check that this is not happening, but it can happen from time to time, especially if there is variation in the product. Then, of course, misuse is very common. People, if you drop your mobile phone into water, this is clearly misuse, and it's an overstress situation in a way, because most mobile phones. Of course, if your phone has been designed to be dropped in the water, it's different. But if not, it's an overstress, it's a higher humidity level than the phone has been designed, especially if there are impurities. So quite often this leads, of course, to a failure of the product, but not necessarily. And high temperature is very common, overstress or too high mechanical stress. Then another way is so this is slowly developing failures. So these are the changes in the structure, in the materials due to use and aging, and finally they cause failures. And I already talked about this, that we can see the stressors and we can see failures in many different processes. So it is important to consider all the stages of the product's lifetime, whether it's manufacturing, as it says here, for example, due to poor process control or poor quality of components, we can have issues, we can have some failures. And quite often you already have to do failure mechanisms to study failure mechanisms or do failure analysis after manufacturing to check why some products fail. And quite often we do check the quality of the products after manufacturing to make sure that these failed products are not sent to the customers. And then, of course, transport, storage, and use, as I already said. And then where we get failures and products for failure analysis is reliability studies. And these can be very, very important because they give us a possibility to really study and understand what's going on in a product and why it fails as it does. And it's important to notice that quite often we have a combination of different stresses from different processes. For example, in manufacturing, we have a reflow cycle, which means high temperature. And then this causes micro cracks in the structure, which we do not see them immediately, but after certain, for example, transportation conditions, they can cause failure. So it's a kind of combination of several things which causes the failures. And this, of course, makes it quite often difficult to determine what is the actual cause for a failure. Now, I also want to mention intermittent failures, because this is something we see very often, especially in electronics and electrical engineering. This is something which happens easily. So what intermittent failure means is that the failure is not permanent. We see failure, for example, at certain conditions. For example, at high humidity, we have a failure, but then when the product dries, the failure is not there anymore. It might not be repeatable, but quite often it is. But it means that we need to know what is the reason why this happens. And one example is cracks in interconnections, which quite often cause a situation where in some certain conditions, the product works okay, but in some other it does not. And for failure analysis, this is really difficult, because what can happen is that you get the product from the field where it has failed, but when you get it to the lab where there is controlled humidity and temperature, you don't see anything. And you need to know what are the conditions to try to repeat them and get the failure again. And many analysis techniques don't give you the possibility to use different conditions. So this can be very, very difficult. Then I also want to mention quickly here the reliability testing. As I mentioned, it is a very good way quite often to understand why things fail and how they fail. And it's commonly used when we do research and development, design new products. However, there is one thing which is quite common, is that even in this stage, validation testing is used, and validation tests are normally quite short pass or fail tests. It means that they are used to check that the product fulfills the requirement of the test. So there shouldn't be any failures. If there are, we need to do some improvements. But the problem with this kind of testing is when it's used in product development is that we don't get any failures. We have no idea how things fail. And then if you get something back from the field, there are failures. You don't have this very, very important information about what kind of failures you expect in different conditions, and you can immediately check if there is a correlation and so on. So it's very, very beneficial to start to test until you see failures when you do product development. And also in this way, we can see when the failures start to occur, so we can do some reliability prediction and also compare that to the field data. So then to the actual stressors. There are several, of course. And here are some typical ones. So we have electrical stressors, thermal stresses, humidity, chemical, different impurities, mechanical stresses, radiation. For example, UV light is a very, very common source of problems for polymer materials, which needs to be tested. Then we have dusts and other problems like these, and of course biological. I'm going to talk about in more detail some of these, not all. So for example, not going into biological ones, this can be quite exotic from time to time. So you can have some mold growing, which causes problems, but also animals eating the cables and so on. So these can be quite difficult to predict and know. And so they are quite a challenge, also from testing perspective. Anyway, so thermal failures, meaning that failures caused by high or low temperature or fluctuation of temperature. And this is a very, very common problem in many fields and causes lots of problems. And of course, if we consider why we have temperature fluctuation or different temperatures, is that the environmental conditions, so where are we using the product, is very important. If we are using a product outside, in some areas this means quite constant temperatures. But for example, here in Finland, we are talking about very low temperatures and also high temperatures and changes and so on. And also if we are working, for example, in close to some motor, for example, in a car, you can have very high temperatures due to the environment where the product is. And then, of course, we have also internal heating, which causes temperature fluctuation. And especially in electronics, for example, it is very common that the components, when they are used, they can be can have very high temperature, and then when they are not used, the temperature, of course, reaches the level of the environment, and this can cause lots of fluctuation during the product's use, which is very important and most likely the most typical reason for failures in electronics. So both high and low temperature may be critical, and normally thermal shocks and fluctuations are the most critical ones. And so the reason why, for example, high temperature causes failure so often is that it changes the properties of materials. And normally the mechanical properties, for example, are decreased. This means that the mechanical strength is not as good, especially with polymer materials. So at high temperatures, the polymer material may change its properties, and then this can lead to failures. It also affects many electrical properties, which can cause issues and, for example, lead to then electrical failures, which again cause then other problems and so on. And also many chemical processes are, their rates are increased, so chemical reactions happen faster. This can have lots of problems in many products. Sometimes the changes caused by high temperature are permanent and sometimes not. So sometimes when you go to lower temperature, the properties return to the same values, but quite often they are permanent changes. And so this needs to be taken into account when a product is designed in order to prevent failures due to this happening. So for example, in electronics, diffusion happens a lot faster at high temperature with, of course, all applications. So in the picture here is the idea that you have different small atoms going into the structures, and this happens faster when you have high temperature. And for example, in electronics, this means that we have in solder joints growth of intermetallic layers, which are fragile and then can cause the whole joint to be rather fragile and then cause failure eventually. Polymers oxidize due to high temperature. They also quite often become brittle, and then they are easily cracked and cause failures. So then to the mechanical stresses. And this is also another very, very common reason for failures. So we have two different types. We have dynamic stresses, and then we have static stresses. And the dynamic means that the stress is changing constantly, for example, due to vibration, which is common. For example, in a car, when you are driving a car, there is lots of vibration in different parts. Parts of the car have different vibration kind of environments, and these can cause lots of stresses, and then also, of course, failures. There can also be, shocks is not really that good here, but thermal shocks and thermal cycling. So fluctuation of the temperature causes also mechanical stress. I will have more about that in the next slide, I think. Then we have the static mechanical stresses, which means that the structure is constantly under stress. For example, if we stretch elastic band and keep it like that, it has a static tensile stress, which eventually causes, if it's high enough, it causes the elastic band to break. So for example, quite often in polymer products, this can be an issue that they are poorly designed, there is too much stress, and eventually it causes a failure. Or for example, a casing or something like that. So we have lots of different issues here. There can be cracks, the structure can bend, it can buckle, meaning that when you have lots of stress and it suddenly gives in. And then, of course, we also have wear of the surfaces and fretting when we have dynamic stresses. So, for example, here in the picture, there are cracks in aluminium films on top of a polymer films. And this is now due to actually thermal cycling. So a bit more about that. I think it's actually, sorry, it's in the next one, not this one. But anyway, so that was the fatigue failure I showed in the earlier slide. So when we talk about mechanical stresses, it's very, the fatigue and creep are very, very important. So fatigue is due to these dynamic stresses, fluctuation of stress. And basically what happens is that we have a structure which has a fluctuation of stress, and it doesn't need to be very high. So a single exposure to such a stress doesn't really cause anything. But then when we have thousands or even millions cycles, eventually the structure will fail and crack. So this kind of fatigue cracking is probably the most common reason for failures in most of the use areas. Creep is another mechanical phenomenon which is very common. So here we have, especially with polymer materials and also low temperature metals, here we have a situation that we have a stress. For example, we are starting to stretch that elastic band, and it will start to give in. So it will change, it will creep, it will eventually, the polymer chains in the material will align them differently so that they can absorb the stress and this way lower the stress the material is exposed to. And this again eventually leads to cracking. And both are very, very important in failure, reasons for failures due to mechanical stresses. Stress relaxation is quite similar to creep. So in that one, we have permanent strain. So we have, for example, a part which is constantly bent a bit, and the polymer chain again start to change their positions in the structure so that the stress is reduced, and eventually this can lead to crack. So it is important to consider these when when products are designed, but also in failure analysis, quite often we need to consider these. So I already mentioned the thermal cycling, and said that I'm going to talk about a bit more about that. So fluctuation of temperature is one of the main reasons for failures. And basically what it causes is that all materials have different expansions due to temperature, so thermal expansions. And then when we have fluctuation, some materials expand a lot more than the others, and this causes internal stresses to the device or product, whatever we have. And nowadays, quite often, it is more common to have a structure where we combine different materials. We can combine polymers with metals or ceramics and so on. And especially polymers have a lot higher thermal expansion than metals and especially ceramics. So we have lots of stresses in the structure. And this causes this kind of dynamic stresses, which lead quite often to fracture due to fatigue. And this is a very, very common way of failure, especially in electronics. So for example, here we have in the picture, we have a crack in a solder joint due to thermal cycling. And what is also important to notice is that the thermal expansion changes, especially in polymer materials, due to temperature. So we have this glass transition point where the polymer material softens, or it can melt, but in many materials it only softens. So we can use the polymer above this point, but it is very important to notice that the thermal expansion increases a lot, and this can cause huge problems in many products. So it is very important to check beforehand, or at least during the failure analysis, if this has happened. So thermal shocks is another, even a bit harsher version of this, but basically point is here that we have very, very fast change of from one temperature to another, which causes thermal gradients in the structure, and is, for example, a typical reason for why plated through holes in printed circuit boards, as shown here, fail. So then another matter causing problems is humidity. This is a very, very typical cause for failures. And it is it's especially harmful when combined with other stresses. So with corrosive impurities, we have, of course, high risk of corrosion. And with temperature, it's a very bad combination for many materials and structures. And basically, there is always some humidity. The point is whether there is enough humidity to cause problems. And if we have fluctuation of temperature combined with humidity, this can cause condensation. So there is actually water droplets forming on top of the surfaces, which can be a major issue, especially in electrical systems. So one important point is that some materials can absorb moisture. This does not really happen with metals and ceramics unless they are designed to absorb moisture. But with polymers, the polymer change normally form a structure which leaves lots of open space inside the material itself. And this means that water can absorb into the space inside the material in between the polymer change. And this can markedly affect the properties of the polymers. And especially at high temperatures, the absorption is increased. So what the water causes in polymers is, one is delamination, because water goes to the interfaces. So for example, if we have metal polymer interface, this interface can open and then we have delamination. Also, this water causes swelling of the polymer, which can cause bending or different stresses in the structure or even cracking. And then there are some other processes, for example, hydrolysis of polyesters and polycarbonates, which basically breaks the material and can cause really sudden, not really sudden, but failures due to embrittlement, which can be quite problematic. Then corrosion is, as I mentioned, quite often related to humidity, but also a big issue in many, many areas, and very typical reason for failures. So we very often have impurities, and there are many reasons for those. Well, if you are in coastal areas, salt is normally present, which is very corrosive. Air pollution is a problem in many areas. In most urban areas, you have some air pollution. In some urban areas, there is lots of air pollution, and there is then you have sulfuric compounds and also nitrogen dioxide, which are all corrosive. Also, chlorine is typically present then. Industrial environments, some of them are very, very bad. For example, water treatment plants are very, very difficult environments from corrosion perspective. And then we have, of course, materials and processing, which is important to remember that when a product is done, there is impurities quite often present from the materials used and so on. Of course, one of the worst sources of impurities is human. For example, putting your finger on top of an electric circuit is a certain way to cause corrosion. So there are lots of sources, and sometimes it can be very difficult to find what the real source for corrosive impurities really are, and it can take lots of work to find where it comes from. So corrosion may occur when we have humidity and these impurities. It does not always occur, but quite often it does. You don't necessarily need to have these kind of conditions. Also, mechanical wear or high temperature can cause corrosion. So you don't always need humidity and chemicals to do that. There are several corrosion types. I'm not really going into them. So because corrosion is a very, very complicated process, and there are lots of possibilities here. But some examples, for example, uniform corrosion means that corrosion of a whole area. For example, when you see an iron component made of iron, which is fully, the whole surface is covered by corrosion products, that's uniform corrosion. Then important processes, for example, are pitting corrosion and crevice corrosion. And what makes these important is that there is a small hole or crevice or some kind of location, and there, even though you don't have necessarily overall very corrosive environment, in these small locations, the corrosion can start to occur very, very quickly and then lead to failures. And especially in electronics, this is a problem because under components, there are normally places where this can happen. And this can then lead to corrosion failures very quickly. Galvanic corrosion is probably the most well-known and very common corrosion process. Basically, it means that we have two different metals next to each other, and then the less noble one starts to corrode, and this again can happen quite quickly. And sometimes there are ways to prevent it, but sometimes you just cannot do that, and that then you need to check, is it a problem or not. So this is common in electronics, where we use lots of different metallic layers on top of one each other. So they're a very common corrosion method. Another common corrosion in electrical applications is fretting corrosion. Now, this is an example of corrosion where we don't have humidity involved, where basically this can happen, for example, due to vibration, where surfaces are repeatedly, they move against each other, and this leads to oxidation of the surfaces, and eventually you have lots of small oxidized particles. For example, here we have a layer of oxidized particles, which caused the resistance of this contact increase. Here is another example. So this is very common in connectors and other similar surfaces which are used for electrical contacts and which can move, for example, due to vibration. So this is a very common failure mode too. Then I'm not really going to talk that much about the electrical stresses, but these, of course, are, if you are working with electrical devices and structures, these are very important. And we have electrostatic discharge, so ESD failures, and other electrical failures due to, for example, overstress. So these cause lots of failures, and there are different reasons for this. And of course, when you have, for example, corrosive environments, there can be some combination of corrosion with different electrical problems, and they kind of make things happen faster. So, for example, copper anodic filament, which is basically corrosive. Here is in the picture below. These are glass fibers from printed circuit board, and here is copper wire. So the copper starts to grow along the glass fibers and forms shorts and so on. So there is lots of different possibilities for electrical failures. Okay, then I will very quickly go through the analysis methods. I'm sorry, I'm a bit late in my webinar, but as I said, Sanna is going to talk about these a lot more in the next week, so I will be very quick with these. What I want to say, however, is that when we start to do analysis in failure analysis, it is important to start with non-destructive methods, if possible. And the reason for this is that when we start with non-destructive methods, we can analyze the same structure with different methods. And if we find the failure, we can maybe fix the equipment and check if this really was the reason for the failure. So this is very beneficial. However, if we are talking about more complex structure or more difficult failure, normally we need destructive methods to find the real reason for the failures. And this means that we need to, for example, cut the part or do something else to it to analyze what has happened. And the more complex the structure is, the more complex is normally the failure analysis and more techniques we need to use. So for non-destructive methods, there is visual inspection and also electrical functionality testing if we are talking about electrical systems, which can be very beneficial, but also very time-consuming. And in this, it is important that someone knows exactly how the device actually works, so we can look really where the failure has occurred. Sometimes also checking the temperature can be really, really useful for finding the failures, but this can be a bit more challenging. Then about non-destructive methods, X-ray is commonly used to study metallic structures, and it's commonly used in electronics and electrical engineering. So basically what we can do with this is check that all the components are where they should be, that the attachments made with soldering, for example, are as they should, and so on. So it can be used to check is everything as it should, and is there failures or not. For example, here is a crack in a plated through hole in a printed circuit board, which can be seen in the X-ray analysis. This is not really good then for checking, for example, polymer materials. Now microscopy is here, although quite often we use it as a destructive technique, but especially optical microscopy can be also used to do more detailed visual inspection, and is often very useful to do that. Electron microscopy, so SEM, for example, is more detailed. This is a picture taken from a corroded wire with SEM, but typically we need to use this as a destructive method. But it gives more detailed analysis of the materials, for example, all the surfaces, all failures, and so on. Another non-destructive method, which we use a lot, for example, is SAM, so scanning at acoustic microscope, and it's based on using sound to ultrasound wave to study if there are some problems with a sample, or are the components where they should be. And here is an example. So this is before testing, the upper picture, and lower picture is after testing, and the white area shows us where the delamination has occurred. So this is one of the uses. We can also see quite often cracks, voids, air bubbles, without destroying the sample. So we can analyze, for example, during the testing, how delamination occurs in packages and so on. So this can be very useful method. Then for destructive methods, we have mechanical methods where we destroy the sample, of course, and quite often we need to use this to compare materials from a failed and not failed sample. But it can be very useful to check that has something happened which caused the failure. For example, the adhesion strength has lowered, or there is some other changes in the mechanical properties which are critical. Then we have decapsulation and cross-sectioning, and these are probably the most used methods in failure analysis. So basically what we do is that we do a cross-section using different methods of the product, and then we analyze what we can see from that. And the main point is that here we can go to the internal structures of the product. And here you can see some pictures, for example, of a solder joint where it is easily seen that there is a crack, and we can see that where the crack goes and how it has happened. So this is very, very commonly used. The most typical way to do cross-section is mold the studied structure into epoxy, for example, and then grind and polish it to the place which we want to study. The problem here is that we can only check one place. And I'm not going to talk about material characterization, so check the webinar next week for more details about that. So I will skip directly to accelerated testing, just mentioning that it is also a tool for failure analysis. And sometimes you need to repeat the conditions which caused the failure. So then we use accelerated testing, and this can be extremely beneficial to really check why the failures happened. And we can use some supporting techniques like design of experiments to make it even more powerful tool. But of course, this is time consuming and expensive. But then when you really need to find out what's going on, we quite often need to do this also to support our failure analysis. Okay, so that was my webinar, and I will just give a quick summary of what I was talking about. So failure analysis is very, very important part of the reliability analysis. And since the products we nowadays have are very complex and contain numerous different materials and structures, so it's very, very important to do failure analysis, but it's also often very challenging. And because of this, we can have lots of different failures and sometimes very surprising failures. So it's important to keep an open mind when you're doing failure analysis and really be open for possibilities which you did not consider in the beginning, the most likely ones. And quite often we have a combination of different factors which can make analysis very, very difficult and time consuming. But it is very, very important that we have a systematic approach which can give us information of the real failures and how they can be fixed. And so thank you all for joining, and sorry for being a bit late with this. As I already mentioned several times, we have a next webinar coming in next week about material characterization, and Sanna Lahokallio is going to talk about that. So please join. It will be an excellent webinar. So thank you all and goodbye.